Hi, my name is Andrew Conrad, and today I'm going to be talking to you about drone-based quantum key distribution. I'm one member of a very talented team of researchers at the University of Illinois at Urbana-Champaign and our collaborators at The Ohio State University, led by our fearless principal investigator, Professor Paul Kwiat, and our fearless co-PI, Professor Dan Gauthier. You're probably very much aware of the increasing use of drones in our modern-day society. Drones typically are used for photography and cinematography, as well as defense applications. But emergent drone technologies include ferrying humans using drone taxis and wide-scale package delivery. Moreover, the first use of drones to deliver the COVID-19 has been demonstrated earlier this year. While drones offer new advantages over manned vehicles, such as automation and reconfigurability, they are susceptible to new types of attack vectors that wouldn't be present with humans in the loop. For instance, drones suffer from signal spoofing, both for their command and control signals as well as their sensor inputs. Additionally, denial of service attacks can bring down drone networks, again, both with the command and control signals as well as the sensor inputs. For example, both of these types of attacks were successfully used to capture an RQ-170 drone last decade. Quantum approaches, such as quantum key distribution, can offer improved security over classical approaches for securing future drone constellations. Moreover, the technology needed to establish quantum key distribution links between moving drones can be leveraged for other mobile reconfigurable platforms, such as ships, planes, and satellites. Other researchers have demonstrated entanglement distribution from a drone to two ground stations, as well as a drone to two ground stations, which is relayed using another drone. We're seeking to be the first group to demonstrate drone-to-drone QKD. Additionally, we want to be able to have the entire system contained within the drones without using ground stations. So what sort of hardware do you need to actually demonstrate drone-to-drone QKD? Well, obviously, first, you'll need a drone. And for us, we employ the DJI S1000 Plus drone, which is pictured here. Second, you'll need a compact QKD source, one that can fit within the size, weight, and power constraints on board the drone. Additionally, you'll need TX and receive optics, and some way to transmit single photons from one drone to the other drone while they're in flight. So you'll need a pointing, acquisition, and tracking subsystem. Additionally, you'll need single-photon detectors, a time tagger, and then a way to synchronize the clocks of the two drones while they're in flight, which can be a challenge because they're in constant motion relative to each other. So next, I'm going to go through each of these critical subsystems in more detail and give you characterization data. The first critical subsystem that you need to do drone QKD is obviously a drone platform. Here, our research team utilizes two different drone platforms. The first one is the S1000 Plus drone, which is produced by DJI and is based in China. It has a max power consumption of around 4 kilowatts and a max payload capacity of about 6.6 kilograms. The second drone platform that we use is the Alta 8 Pro, which is produced by FreeFly Systems and is based in the US. It has a max power consumption of around 7.6 kilowatts and a max payload capacity of around 11.9 kilograms. Unfortunately, both drones suffer from limited flight time using their onboard batteries, which can make doing long-term field testing a challenge. So the research team developed our own power tether system that can effectively keep the drones in the air for as long as we want to do testing. The next critical subsystem that is required is a compact QKD source. And here we partnered with our collaborators at The Ohio State University to develop a resonant cavity-based 3-state decoy state QKD source using laser technic LEDs. So because we're using 3 different LEDs, the outputs from these LEDs needs to be indistinguishable in all degrees of freedom, except for the encoding polarization, which is what we're encoding our states with. So the first thing that they need to have is spectral indistinguishability, and great care was taken to ensure that the signals and decoy states are spectrally indistinguishable from each other, which you can see here. In fact, if you're more interested in getting to the details of this source, you should check out poster 209 in the poster session of QCrypt, which our collaborators discuss in greater detail how they achieved spectral indistinguishability with their sources. In addition to spectral indistinguishability, temporal indistinguishability is required for the QKD pulses that are produced by our source. And an FPGA is utilized in the source, and we employ phase lock loops to very precisely control the phase and the pulse width of the pulses that are produced by the LEDs. And as you can tell here, we have very good temporal overlap between the pulses produced for both our signal and our decoy states. Here's a view of the actual hardware used for our QKD source. This is an FPGA board, and it uses an Altera FPGA. This green board right here is a custom daughter card, which interfaces with the actual LEDs. The LEDs are held inside these custom fabricated 3D printed mounts, and these set screws provide fine tuning to maximize the output light coupled into single mode fibers, which go off the screen here. In addition to developing a resonant cavity-based compact QKD source, we're also developing an alternative QKD source that is more secure to side channel attacks, and it's based on a polarization modulator. The basic premise of the device is as follows. We take a polarization modulator with the incoming PMF fiber that's keyed at an axis of 45 degrees with respect to the fast axis of the KTP crystal. What effect that has is that it launches diagonally polarized light through the crystal. And by suitable choice of voltage on the KTP crystal, we can apply a phase to rotate the polarization to either right circularly polarized light or left circularly polarized light. Alternatively, if we take no action, the light will maintain its diagonal polarization through the crystal. Thus, 3 different QKD states can be produced using this scheme. And the advantage is that any fluctuations in the source's temporal or spectral properties are manifested through all of the QKD states, thus making it more immune to side channel attacks. Here, we measure the fidelities of the target states along the right and left circular polarization, as well as a linear polarization state. And as you can tell, the quantum bit error rates are hovering just over 1% for right and left circular polarization and around 1.2% for the linear polarization. The implementation of this approach is as follows. We have a pulse laser here, which produces pulses in time, and then it goes into a polarization modulator, which is used to act as an attenuator to produce the different amplitudes which are required for the decoy state. Next, it goes into the polarization modulator in order to produce the right, left, and linear polarization state, which is denoted here. After the drone and the QKD source, the next critical subsystem are transmit and receive optics. Transmit optics are required to prepare the quantum states and then transmit them through free space, while receive optics are required to collect them and then perform the polarization projection measurements, which are required for the QKD protocol. Because weight and size are such large constraints on the drone, we opted for custom 3D printed bench designs that have components both on the top and the bottom. As you can see here, this is a 3D model of our design, and it includes projection measurements as well as supporting hardware, including fast steering mirrors and IR cameras for the pointing acquisition and tracking system. Let's look more closely at our transmit bench in more detail. If we look over here in this area, this is our state preparation optics, which are used to create both the left and right circularly polarized states, as well as our linear state for air checking. Now, because they're produced by 3 independent LED sources, they need to be spatially overlapped in order to prevent side channel attacks. For instance, if they weren't, then an eavesdropper could merely measure the spatial mode of the photons without measuring their polarization and could ascertain the individual states. So in order to eliminate this as a side channel attack, we couple all of the states through a single mode fiber in order to have them have the same output mode. Unfortunately, the single mode fiber will perform a random unitary transformation on the polarization state. And since we're encoding in the polarization state, that's a problem. So we have compensating wave plates which are applied before going through the spatial mode filter. After that, the light goes through a narrowband filter and then passes through dichroic mirrors, which are used to extract and inject beacon signals for the pointing acquisition and tracking system. The outgoing light bounces off two fast steering mirrors and then propagates through the free space channel. Now, let's take a look at the receive optics bench hardware in a little bit more detail. The architecture is similar to the transmit bench architecture. The incoming photons through free space enter the apparatus here, bounce off two fast steering mirrors, and then transverse through two dichroic mirrors, which are used to extract and inject beacons which are required for the pointing acquisition and tracking system, respectively. The quantum channel then goes through a narrowband filter and then enters our state projection measurements. A 50-50 beam splitter is used to randomly select the basis projection between HV and right-left basis. And then they are collected and then coupled into multi-mode fiber, which are then processed. Here's what the transmit and receive bench looks like for a stripped down version of the bench, which is used for pointing acquisition and testing purposes. You can see here the incoming light comes into the aperture, bounces off fast steering mirrors, goes through our dichroics, and then is received by a single collimator. On the flip side of this bench, if you look on the other side of these dichroic mirrors, the light comes up and bounces off 45-degree mirrors onto an angular resolver here, which is required for the pointing acquisition and tracking system. And then we have an outgoing beacon that goes through the other channel. And if you look on the front, we have some IR cameras and IR beacons, which are also required for our pointing acquisition and tracking system. So once you have a drone and a QKD source, as well as transmit and receive optics, the next critical subsystem you need is a way to reliably get single photons from one drone to another drone while they're both in flight. And that can be a rather challenging job. So it requires a pointing acquisition and tracking system. Now we segmented our pointing acquisition and tracking system into two smaller subsystems. We have a coarse alignment phase and then a fine alignment phase. The coarse alignment is what we call the outer loop, and it uses IR beacons and IR cameras in order to provide coarse pointing accuracy. This is one of our older bench iterations, but you can kind of see on the transmit drone, we have an IR beacon, which is picked up by an IR camera on the receive drone. Correspondingly, we have an IR beacon that's transmitting on the receive drone, which is seen by an IR camera on the TX drone. Now, we use some spectral filters and do some image processing in order to ascertain the centroid of the other drone in the camera's field of view. And here's an example of what that looks like. So this is a photo taken from the TX drone looking at the RX drone and what it sees. Now when the drones are in flight, random turbulence due to the drones induces pointing errors, and the outer loop works to adjust the gimbal to keep it generally looking at the other drone, and that goes in both directions. You can kind of see what the IR beacon looks like over time while the drones are in flight. It kind of has a bit of a random trajectory, and then the control system is working to minimize the error between the set point, which is located here with a red X, and the current position. So once the outer control loop is able to establish a coarse pointing at the other drone, then control is handed off to our inner loop, which provides fine adjustment to maintain the line of sight between both drones while they're in flight. Now the architecture for our inner loop is presented here. Essentially, on the transmitter, we have a TX beacon at 705 nanometers that gets mixed into our quantum channel using a dichroic mirror. It then propagates through the fast steering mirrors and out into the free space channel. That beacon is then received by the receiver and then is stripped off using a dichroic mirror and is sent to an angular resolver, which uses a position-sensitive diode. Conversely, an outgoing beacon at 520 nanometers is transmitted from the receiver and is mixed in using dichroic mirrors and travels back to the transmitter, is picked off using another dichroic mirror, which goes to a position-sensitive diode. Additionally, the fast steering mirrors that we have employ absolute magnetic encoders, and we added a long-range zoom camera that can look at the other drone's position and provide offsets from the fast steering mirrors so that we can quickly acquire and reacquire the target, at least to get the beacon onto the PSD. And once the beacon is on the PSD, our control feedback then controls the two fast steering mirrors in order to keep the line of sight centered while the drones are in flight. So let's look a little closer at the inner loop's angular resolver sensor. Quite simply, it's just a focusing lens and a position-sensitive diode. We have some other components to block out the other signals using a bandpass filter, and we also have a stop aperture. But the basic idea is as follows. The system determines the incoming angle of arrival of the other beacon, and then it directs the outgoing beacon to exit at the same angle that the incoming beacon is arriving at. And here's an example of what it looks like on the PSD and when we control it with our fast steering mirrors. So here we're changing the set point of the PSD on the active surface area into a 4x4 grid pattern. And the blue dots are the instantaneous angle of arrival coming in that are redirected using the fast steering mirror. So this has the effect that the outgoing beam is creating the exact same pattern that you're seeing, a 4x4 pattern back at the other drone. And we did this for testing and calibration purposes of the inner loop system. Now, in order for this architecture to work, we really need a good one-to-one correspondence between positions on the PSD and incoming angles of arrival. So we performed multiple linear homography tests to ensure if this were the case. And as you can tell on the left-hand side, generally speaking, this is not the case. And what we did here is we had 21 by 21 incoming different angles of arrivals, and we just observed what pattern does that produce on the actual PSD. And as you can see, it kind of looks like it's a bit of a flag that is folded over on this side, which generally is bad because this means that we can't ascertain what the angle of arrival is for these positions on the left. However, when we added a stop aperture, we constrained the field of view to reduce distortions from the lens, and we were able to reproduce the 21 by 21 linear homography with very little distortion, and we were able to achieve a one-to-one correspondence, which is required for the system to work. So the next thing to do is actually to test how our performance is with our pointing acquisition and tracking system by propagating a classical laser beam through the channel and measuring the channel loss. So we did that outdoors with both drones sitting on a table at 10 meters apart. And we did this over a sequence of different configurations. So this first part, both the outer and inner loops were turned on, and the blue is the channel loss through the channel using a classical signal, and the red is the noise floor. The second sequence, the inner loop was turned off, but the outer loop was kept on. In this third section, both control loops were turned off, and as you can see, the performance degrades to approximately the noise floor. Then the outer loop was turned back on, thus restoring a good portion of the signal, and then the inner loop was turned on again, thus increasing the signal again, and finally the outer loop was turned off but the inner loop was kept on, which further degraded the channel. So as you can see that the channel loss is minimized when both control loops are operational. After we perform ground locking, the next thing to do is to get the drones in the air in order to test out how our pointing acquisition and tracking system is functioning. And to do that, we first perform ground-to-air locking. In this configuration, the transmit drone is on the ground and the receive drone is in the air. So this is what a picture of our receive drone looked like up in the air, and it has a green outgoing laser for its beacon. And then we measured the classical channel loss of a signal from the ground to the TX drone over time. And this testing was done in a particularly high wind environment, at least high wind for our drones. The winds were gusting around 22 kilometers per hour. And in this configuration, we had the outer loops of both drones on, and the inner loop of the TX drone on, and the inner loop of the RX drone turned off. And then this is our channel loss as a function of time, as compared to the noise floor. After performing ground-to-air locking, the next step is to get both drones in the air and test out how our pointing acquisition and tracking system is performing. So here's a picture of both of our drones in the air on the campus of the University of Illinois at Urbana-Champaign. The drones in this were about 10 meters apart. While the drones were in the air, we transmitted a classical laser signal through our free space optical channel and measured the receive power as a function of time. We normalized this power based on the optical power exiting the TX bench. Next, we calculated the coupling loss as a function of time, and we plotted it here. It represents the channel loss as a function of time over about a 10-minute duration. For this test, the winds were fairly calm, and the drones were approximately 10 meters apart. And we report an average of 27.1 dB of channel loss over this duration. After the single photons are transmitted from one drone to the other drone and undergo polarization projection measurements, the next step are for the single photons to be detected. And for this, we use a commercial off-the-shelf 4-channel single-photon detector, which is produced by Perkin-Elmer. It gives us a 60% efficiency at our QKD wavelength, and it can handle approximately 1.5 million counts per second per channel before saturation. After the photons are detected by our single-photon detector, the single-photon detector outputs a logical TTL pulse. Next, we need to monitor these signals and record at what time a single photon was detected and at which channel. And to do that, we use a fast FPGA-based time tagger. Here, we're using the DE10 standard board. It has a Cyclone FPGA, and it operates around 100 megahertz. It detects and saves individual events along with their channel and the time tag to an onboard SD card for secure post-processing. In order to perform the QKD protocol, both the transmitter and the receiver must have a common time base, which requires time synchronization between the two platforms. However, because the drones are in constant motion with respect to each other, that can be challenging. So we have two different approaches to perform time synchronization between the drones while they're in flight. The first one is a hardware-based approach that uses software-defined radios. Recall that our time tagger uses an FPGA, so we have a daughter card produced by AR Radio that interfaces with the FPGA that produces a timing signal. Now, the advantage with this approach is that the timing signal and the QKD signal both travel at the speed of light, so they'll arrive at the receiver at the same time, regardless of the relative motion of the receiver. And here's an example of the IQ timing spectrum that is produced by the AR radio. In addition to having a hardware-based time synchronization protocol, we also have a software-based time synchronization protocol. The basic idea is as follows. When Alice and Bob exchange their basis information, Bob uses the detection event history and computes a likelihood that the given data came from Alice. He uses a variety of information such as a priori probabilities, mean photon numbers, detector dark counts, and the expected polarization. Likelihoods are then compared using a Bayesian aggregation approach, and then detection events are extracted using a fast Fourier transform function. If you're interested in learning more about this, you should check out poster ID 192, which is presented at the QCrypt conference, to learn more about this approach in greater details. As I mentioned previously, there's a very talented team of researchers working on the quantum drone team, led by our fearless PI, Professor Paul Kwiat, at the University of Illinois at Urbana-Champaign, and our fearless co-PI, Professor Dan Gauthier. And we have a very talented team at OSU and the University of Illinois. I would like to acknowledge our funding agencies, the U.S. Office of Naval Research, as well as the NDSEG Fellowship and the Sochi Fellowship. I want to say thank you for your time, and I look forward to hearing your questions.